am M.K. Srivastav of the Department of Physics, IIT Roorkee. This is the second lecture of the 5-lecture series on polarization. In the last lecture, which was the first one, we considered Maxwell's equations leading to electromagnetic waves. We then considered the meaning of polarized light, polarization by reflection, refraction and scattering. We studied Brewster's law and considered working of a polaroid. In the present lecture, which is the second one of the series, we shall take up Malus' law and then shall consider superposition of two electromagnetic waves under different conditions. Different conditions means different amplitude, different phase differences and things like that. Law of Malus. Consider an unpolarized beam of amplitude A and intensity I naught, which is proportional to the square of the amplitude, as we know, incident on a polarizer. Let the incident light have components Ax equal to A cos theta and Ay equal to A sin theta along the axis, with theta varying randomly as the light is unpolarized. Let the path axis of the polarizer making an angle alpha with the x axis. The polarizer, as we have seen, is a device which allows the light wave with electric vibrations parallel to the path direction to pass through without attenuation essentially, and absorbs the light wave with electric vibrations perpendicular to the path direction. The long arrow in the figure making an angle alpha with the x axis indicates the path direction of the polarizer. The intensity I of the transmitted beam through the polarizer can be obtained by taking the projection of the components Ax and Ay along the path direction. As the intensity is proportional to the amplitude, we have the intensity I is proportional to the square of Ax cos alpha plus Ay sin alpha, which means it is proportional to A square times the square of cos theta cos alpha plus sin theta sin alpha, which means proportional to A square times cos square theta cos square alpha plus sin square theta sin square alpha plus twice sin theta cos theta sin alpha cos alpha. Now, as the angle theta varies randomly in the unpolarized beam, the average values of the terms appearing here, cos square theta, sin square theta and sin theta cos theta, are needed to evaluate the above expression. These average values are, for cos square theta the average value is half, for sin square theta again the average value is half. You see, these averages are taken over a complete cycle. Then the average value of sin theta into cos theta again over a complete cycle is 0. This leads to the intensity is now proportional to A square times half of cos square alpha plus half of sin square alpha, which means it is proportional to half of A naught square, and we get the final result that I is equal to half of I naught. The intensity of the transmitted beam Remember, the incident beam is unpolarized. So, the intensity of the transmitted beam is thus half of the intensity of the incident unpolarized beam. And another thing, this result does not depend on the orientation of the path direction of the polarizer, that is, it is independent of the angle alpha, and the transmitted beam is plane polarized with electric vibrations along the path direction of the polarizer. If the incident beam is plane polarized with electric vibrations making an angle theta as before, but now this angle is fixed with the x axis, and the path direction of the polarizer makes an angle alpha with the x axis as before, the intensity of the transmitted beam is again given by the same expression, that is, the intensity is proportional to the square of Ax cos alpha plus Ay sin alpha, which means it is proportional to A square times cos theta cos alpha plus sin theta sin alpha squared. So, it is proportional to A square times cos square of theta minus alpha. So, therefore, the intensity I is equal to I naught times cos square of theta minus alpha. You see, no averaging need be done now, because the angle theta is fixed, the incident light beam is polarized. The intensity of the transmitted beam now we find thus varies as the square of the cosine of the angle theta minus alpha, the angle between the plane of vibration of the incident beam and the path direction of the polarizer, working here as an analyzer. This is called law of Malus. Now, if a plane polarized beam polarized along the x axis by the polarizer P1 is incident on another polarizer P2 here, and if this polarizer is rotated about the beam direction, then the intensity of the emergent wave will vary according to the above law. For example, if the polarizer P2 is rotated in the clockwise direction, then the intensity will increase till the path axis is parallel to the x axis. A further rotation will result in a decrease in intensity till the path axis is perpendicular to the x axis, where the intensity will be almost 0. If we further rotate, it will pass through a maximum and again a minimum before it reaches its original position. The emergent light, after passing through the polarizer P2, is now polarized with the direction of electric vibrations parallel to the path direction of P2, working here as an analyzer. Let us now consider superposition of two waves. Consider the propagation of two plane polarized electromagnetic waves, both propagating along the z axis, that is the same direction, with their electric vectors oscillating along the same direction, that is the x axis one. The electric fields associated with the waves can be written in the form E1 equal to A1 cos of kz minus omega t plus theta 1, and E2 which is A2 times cos of kz minus omega t plus theta 2. Both of these fields are along the x axis. A1 and A2 represent the amplitudes of the waves, and x hat represents the unit vector along the x axis theta 1, theta 2 are arbitrary phase constants. The resultant of these two waves would be given by just the vector addition. So, E is equal to E1 plus E2. Now, this can always be written in a form like this: E is equal to A times cos of kz minus omega t plus theta along the x axis naturally, where this A is given by the square root of A1 square plus A2 square plus twice A1 A2 times cos of theta 1 minus theta 2. This A represents the amplitude of the resultant wave, resultant of the superposition of the original two waves. We observe that the resultant is also a plane polarized wave with its electric vector oscillating along the same direction along the x axis. Let us now consider superposition of two plane polarized waves, both propagating along the z axis, but with their electric vectors oscillating along two mutually perpendicular directions. Earlier they were along the same direction, now they are mutually perpendicular directions, say along the x axis and along the y axis. Remember, both the waves are propagating along the z axis. So, we can write E1 is equal to A1 cos of kz minus omega t, this is along the x axis. E2 is equal to A2 cos of kz minus omega 2 plus theta along the y direction. The angle theta is the phase difference between these two waves. Now, in order to find the resultant, we consider the time variation of the resultant electric field at an arbitrary plane, just for simplicity, at an arbitrary plane perpendicular to the propagation direction, which is the z axis. This arbitrary plane, without any loss of generality, we can assume it to be z equal to 0, just for simplicity. If Ex and Ey represent the x and y components of the resultant field E1 plus E2, then Ex will be equal to A1 cos omega t and Ey is equal to A2 cos omega 2 minus theta. Now, we eliminate t between these two equations, and for that we rewrite the above expression for Ey as Ey is equal to A2 cos omega t cos theta plus A2 sin omega t sin theta. We can write it as first term remaining unchanged, A2 cos omega t cos theta plus A2 times the square root of 1 minus cos square omega t times sin theta. This can be written as equal to A2 upon A1 times Ex cos theta plus A2 times square root of 1 minus Ex upon A1 squared times sin theta, or this means Ey minus A2 upon A1 Ex cos theta whole squared is equal to A2 squared sin square theta times 1 minus Ex upon A1 squared. We can rearrange this, and when we do this, we get Ex square upon A1 square plus Ey square plus A2 square minus twice Ex Ey upon A1 A2 times cos theta, and all of this is equal to sin square theta. This is the general equation of an ellipse. A general equation of an ellipse is an ellipse with the center at the origin and with its major minor axis making some angle with the coordinate axes. So, this represents in general the result of superposition of two perpendicular vibrations of different amplitudes and a phase difference of theta. For the phase difference theta equal to n pi, where n is 0, 1, 2, this means an integral multiple of pi, 1 pi, 2 pi, 3 pi, 4 pi, the above equation becomes Ex upon A1 minus 1 raised to the power n Ey upon A2 and the whole squared equal to 0, which really means Ey upon Ex, the ratio of the y component to the x component is equal to minus 1 raised to the power n A2 upon A1. In the Ex Ey plane, the above expression represents a straight line. The angle phi that this line makes with the x axis depends naturally on the ratio E2 upon A1. In fact, the angle phi is tangent inverse plus minus A2 upon A1. If A1 is equal to A2, this angle will be 45 degrees. The condition theta equal to n pi implies that the two vibrations are either in phase, if n is even 0, 2, 4, which means theta is equal to 0, or a phase difference of 2 pi, 4 pi, 6 pi, or completely out of phase, which means n is equal to 1, 3, 5, the phase difference theta is equal to 1 pi, 3 pi, 5 pi, like this. This means a phase difference of half a vibration or 3 half vibrations or 5 half vibrations. Thus, the superposition of two linearly polarized light waves with their electric fields at right angles to each other and oscillating in phase or completely out of phase. Okay, just these two conditions, the individual vibrations are perpendicular to each other, but they are in phase or completely out of phase, then the resultant is again a linearly polarized wave with its electric vector in general oscillating in a direction which is different from the fields of either of the two, making an angle of phi with, say, the first vibrations, and this angle phi depends on the ratio of the two amplitudes A2 to A1. For theta not equal to n pi, if the phase difference is not a integer multiple of pi, it is not equal to 1 pi or 2 pi or 3 pi, the resultant electric vector in this case does not oscillate along a straight line. This figure shows the resultant for different values of theta, theta equal to 0, pi by 3, pi by 2, 2 pi by 3, theta equal to pi, 4 pi by 3, different values up to a value of 2 pi, a complete range of theta varying from 0 to 2 pi, corresponding to the simpler case when the amplitudes are equal, A1 is equal to A2. We shall consider these cases in a little more detail. The sections A, E and I of this figure correspond to theta equal to 0, pi and 2 pi respectively. A corresponds to theta equal to 0, that is the two vibrations are in the same phase. Remember here the amplitudes are equal, A1 is equal to A2. The E corresponds to theta equal to pi, they are completely out of phase, a phase difference of half a vibration, and I is again when the phase difference is 2 pi, which is essentially means phase difference is 0. These are the situations, as I pointed out earlier, when the vibrations are in phase or completely out of phase. We have already considered these cases. Let us consider now a simple case corresponding to theta equal to pi by 2. That is very interesting. The difference is of a quarter vibration. Ex A1 cos omega t, Ey A1 sin omega t. Remember A1 is equal to A2. Ex has a cos omega t and Ey has a sin omega t. The phase difference is of pi by 2. Ey upon Ex comes out to be 10 omega t. If we plot the time variation of the resultant of these two, we would find that the tip of the electric vector rotates on the circumference of a circle of radius A1. Ex square plus Ey square is equal to A1 square in the anticlockwise direction. The propagation of light is in the positive direction of that axis. This has been taken here to be coming out of the screen. Such a wave is known as the right circularly polarized wave, usually denoted as RCP, right circularly polarized, and is shown in section C of the figure. This is the section C. This shows a circular vibration, circular because A1 is equal to A2 and it is anti-clockwise direction. Remember, the beam propagation is coming out of the screen. The electric vector is rotating in the xy plane in the anti-clockwise direction. For theta equal to 3 pi by 2, now we have Ex equal to A1 cos omega t as before, but now Ey is equal to with a minus sign A1 sin omega t. It again represents a circularly polarized wave as before. However, in this case the electric vector rotates in the clockwise direction. Such a wave is known as a left circularly polarized wave, usually denoted as LCP wave, and is shown in section G of the figure. Again a circular vibration. The only difference with the earlier case C is that here the electric vector rotates in the clockwise direction. Remember, the beam is propagation direction is coming out of the screen. This is called the left circularly polarized. Now, for theta not equal to m pi by 2, so this means this is a case where it is not equal to an integer multiple of pi by 2. In this case, the tip of the electric vector rotates on the circumference of an ellipse. Sections B and D of the figure for theta equal to pi by 3 and theta equal to 2 pi by 3 correspond to right polarized elliptical light. So, this is the REP, right elliptically polarized. So, remember again the A1 is equal to A2, but the only difference here is the phase difference is not just pi by 2 or 3 pi by 2, it is pi by 3, or in the other in the section D it is 2 pi by 3, and that is why the resultant is a journal ellipse whose major minor axis makes some angle with the coordinate axes. So, this is the situation when the phase difference is pi by 3 and 2 pi by 3. Similarly, now the sections f and h for theta equal to 4 pi by 3 and theta equal to 5 pi by 3, they correspond to left elliptically polarized light. These are the given here, section f. Again we have elliptical, the only is the sense of rotation is different compared to the earlier case. And again remember, the amplitudes are equal. So, it is just a wide change in the resultant is found depending on the phase difference between the two vibrations. The two vibrations are perpendicular to each other, their amplitudes are same, equal, A1 is equal to A2. The only difference is the phase difference. If the phase difference is 0 or pi or 2 pi or 3 pi, 4 pi, completely in phase or out of phase, the resultant is again a plane polarized wave, linear vibrations, making an angle of 45 degrees or 135 degrees in this case, A1 is equal to A2. If the phase difference is pi by 2 or 3 pi by 2, this means half a vibration or 3 half vibrations. The result is a circular vibration. This is called a circularly polarized light. Right circularly or left circularly, depending on whether the tip of the electric vector rotates in anti-clockwise direction or clockwise direction. And the general case, when the phase difference is not that simple, if it is pi by 3 in this case as shown in the figure, or 2 pi by 3 or 5 pi by 3, the result is elliptically polarized light, right elliptically or left elliptically, depending on whether the electric vector rotates. Now, as can be seen from the figure, this ellipse in general degenerates into a straight line or a circle, as we have seen whenever theta becomes an even or an odd multiple of pi by 2, as we have seen. But in general, when A1 is not equal to A2, we get an elliptically polarized light wave, which again degenerates into a straight line for theta equal to 0, pi, 2 pi, 3 pi, etc. Remember, theta equal to 0, 2 pi, 4 pi means they are in the same phase, and theta equal to pi, 3 pi, 5 pi means they are completely out of phase. Again, note one thing, that all these different states of polarization which we have considered here, depending on the value of theta, are characteristics of transverse waves only, and electromagnetic waves are transverse waves. So, this is the end of the second lecture. I hope you enjoyed this lecture and also the earlier one. Thank you.